All right, guys, we're starting chapter 10. So we are leaving triangles. We're actually done with them for the year, aside from like triangular three-dimensional shapes, but that's not till later. Let's see what circles have for us ahead. Okay, so some first page is going over some common vocab. So a circle is a set of all points in a plane that are equidistant from a given point called the center of the circle. So a circle with center P is called circle P. So we would call this circle P. We can either write it like this, circle P, or it's a circle with a dot in the middle in P. That's how we would label that. Okay, so now some elements of a circle, some things that we're familiar with. A radius is from the center to any endpoint on the circle. That's this here. Excuse me. A chord is a segment whose endpoints are on the circle. Okay, so for instance, that's a chord. Now, if the endpoints not only are on the circle, but they also pass through the center, it's known specifically as a diameter. Okay, so a diameter is a chord. It's a specific type of chord. Now, those ones I believe you're probably pretty familiar with. Now let's talk about a few new ones. So there's this term called secant. It's a line that intersects a circle in 2 points. So it's basically a chord that's extended because it's a line. It's not a segment, it's a line. So a secant continues on. Then we're going to see this word we've seen before, tangent. And actually there is a connection between tangent, the trig function, and tangent that we're talking about here. So there's a relationship between why they call them what they do. But a point of tangency, or a tangent, let's say that first, it's a line in the plane of the circle that intersects the circle in exactly 1 point. So for instance, they have this here. Okay, so this is a tangent. We can say that BA, line BA, is a tangent, okay, or line AB. Now, the point of tangency is this point B right here. That's where that line touches that point right there. And then a tangent ray, it doesn't have to just be a line, it could be a ray or a segment. So we could also say that we have tangent ray AB or BA, depending on which way we're going. If it's AB, it would be from here, we know, going that way. That would be a ray. Or right at the point of tangency over, that could be ray BA. And then we also have tangent segment, which would just be this piece right here. As long as it touches the circle at 1 point, and only 1 point, it's called a tangent. Whether it be a line, ray, or a segment, you can differentiate. So let's just classify a few. Tell what we have best described below. So AC is right here. This is going to be a radius. Letter B is line. Pay attention to the symbols here. So that was segment AC. Sorry, this is segment AB, not line. Segment AB, and that's going to be a diameter. Next we have ray. My brain is not saying, my words aren't saying what my brain is thinking. Ray DE. So that's from here all the way down. So this is a tangent ray. And then we have line AE. AE is right there. And this is going to be a secant. Now they're asking us here what word best describes segment AG. AG is just from here to here, so we would call that a chord, C-H-O-R-D. What word best describes segment CB? That's going to be a radius from the center point to an end point on the circle. And lastly, name a tangent and a tangent segment. Well, a tangent we can call, how about DE? I know that's the one they said above. We also could have said BE, and make sure we put a line above it if we're calling it a tangent. And then a tangent segment would just be, we could say DB or BD. We can say BE or EB. Those are tangent segments. Okay? All right, we're going to move on. Next page. Now, if it's okay, I'm going to skip this for right now. I want to focus mainly on some of the new parts. So drawing and identifying common tangents. It says here, if we have two circles that intersect, they're in the same plane, they can intersect in one of 3 ways. In 2 points, like we have here, they intersect like this. They can intersect in 1 point, like we see here. They can kind of be one inside the other, or they might share a common point like that. Or they might not intersect at all. That's the third possibility, where they're just 2 separate circles, or Maybe they are one inside of the other. If that's the case, they're called concentric circles. Okay, so they have a common center. All right, now, so 2 points like we had here. If there's 1 point of intersection, I didn't say it before, but they're called tangent circles. They have one line that they both share. There's a tangent line that they both have in common. And if there's no points of intersection, we have concentric circles. Okay, now a line or a segment that is tangent to two coplanar circles is called a common tangent. So that would be something like, let me draw one in. Okay, a common tangent would be something like this. It's tangent to that little circle right there, and it's tangent to the bigger circle right here. That's a common tangent. So there's two types of common tangents. A common internal tangent intersects the segment joining the centers of the circles. So this is a common internal tangent. If I kind of look at this one, I could say this is a common internal tangent. It intersects inside and inside. Internal tangent. Okay, a common external tangent is a tangent, that's what this one is, let's highlight a different letter. Common external tangent does not intersect the segment that joins the centers. So this one that I drew first is an external tangent. This would be an external tangent. These would be external tangents. Okay, so let's draw in some. Tell how many common tangents the circles have and draw them. Use blue to indicate common external tangents. And then we're going to use red to indicate common internal. So this has an external one here. It's hitting at that spot and that spot. And here, that spot and that spot. This one has an external tangent. An external tangent, and this has an external tangent here and here, there and there. Okay, all right, now they want us to identify our common internal tangents. This is going to have 1 and 2, giving us a total of 4 common tangents. This has 1 internal tangent right there, a total of 3 for that one, and this has no internal tangents because they're overlapping. So this only has a total of 2 common tangents. So these are my overall totals. Okay, alrighty, so moving on. They want us to just do that again. So if they want us to state all of them, we'll do blue again to be our external. So blue would be 1 and 2. This is going to have 1 common one they both share, and this doesn't have any. It's a concentric set of circles. They're concentric circles, so no common external tangents. Now my internal would be here and here. This one does not have any internal tangents because they're one inside the other, and neither does this one. So my overall totals are going to be 4, 1, and 0. All right, so some new concepts there. Now we're going to talk about 2 new theorems, apply them, and that'll wrap up this lesson. Okay, so the first one's called the tangent line to a circle theorem. And this says in a plane, a line is tangent to a circle if and only if, there's that biconditional, the line is perpendicular to a radius. So let's just break that down. So if we have this line here, this is going to be considered tangent as long as it's perpendicular to a radius at its endpoint on the circle. So where the radius hits the end of the circle, as long as that's our point of tangency, and as long as that is where the line's perpendicular, then we can say we have a tangent line. Okay? And the second theorem says the external tangent congruence theorem, that 2 tangents from a common external point are congruent. So we have this point S right here. If we have this point S, then we're able to say that if I draw a tangent line to my circle here, and then to my circle here at endpoints R and T, these are my points of tangency, then these 2 segments are going to be congruent. Okay? All right, let's apply these. So here's where it's used, is segment ST, this piece here. Is this, in fact, a tangent to circle P? Now, it looks like one, right? But we need to confirm that, in fact, this is a right angle. So, in other words, triangles haven't completely gone away. We need to confirm it's a right triangle. So, we're going to use the converse of the Pythagorean theorem. Now, you don't need to cite this, but just so you understand what we're using. So, the converse says that if you can apply the Pythagorean theorem, a squared plus b squared equals c squared, then you have, in fact, a right triangle. Okay, so 35 squared 1,225. So 144 plus 1,225, does it equal 37 squared? And I find out it does. The answers are the same. So we have a right triangle. So because this proves true, then we're able to say that we have a right triangle. If we have a right triangle, we have a right angle, and then we can apply what's called, again, the tangent line to a circle theorem. Tangent line to a circle theorem, and I abbreviated that. All right, so just the Pythagorean theorem stuff. And now let's see this one. Again, applying it, but a little different setup, not as straightforward. In this diagram, point B is a point of tangency, which means that AB is a tangent segment. Find the radius R of the circle. So this must be a right angle here because of that tangent line to a circle theorem. So R squared plus 80 squared, my two legs, should equal my hypotenuse squared. Well, my hypotenuse is this entire segment, 50 plus r. So I'm going to put that in parentheses, squared. Okay, so one leg squared plus the other leg squared equals the entire hypotenuse squared. Now let's just take this, kind of branch it out for a second. This is not, we can't distribute the squared. We want to remember that this means 50 plus r, 50 plus r. And we have to FOIL it, so we get 2,500 plus 50r plus 50r, so that's plus 100r plus r squared. So what I did there was I FOILed. Okay, so I'm going to rewrite my problem. I have r squared. 80 squared is going to be 8 squared is 64, and I add 2 zeros. And then I'm going to rewrite 50 plus r squared, but I'm going to put it in standard form. R squared plus 100r plus 2,500. All right, in this problem, what ends up happening is that my r squareds, I have an r squared on both sides. I can just go ahead and subtract it, but I really don't even need to do that step. I see that they're the same on both sides, so they're just going to cancel out. So that's gone. So now I have 6,400 is equal to 100r plus 2,500. I'm going to subtract 6,400 minus 25. And that's going to give me 39. So I have 3,900 equals 100r. Dividing by 100, I get r equals 39. So my radius in this problem is 39, and we're talking about feet. If I look at it, that seems very logical, and I could check it using the converse of the Pythagorean theorem. I would see if 39 squared plus 80 squared equals 89 squared, and it does. All right, let's see if we can apply that second theorem, which says that we have two, as long as we have a tangent from an common external point, so RS and RT, then these two segments are congruent. So they tell us segment RS is tangent to circle C at S, segment RT is tangent to circle C at T, find the value of X. So I can say that, let's write it all out. By the theorem, we know that RS is going to be congruent to RT. That would mean that RS is equal in measure to RT. So we can substitute in the values of RS, which is 28, and the value of RT, which is 3x plus 4. Solving this, I subtract 4 on both sides. 24 equals 3x, divide by 3. So x equals 8. And that's all they wanted us to do there, so we're done. Okay? All right, let's try just setting up these last three. Is segment DE tangent to circle C? So the converse of the Pythagorean theorem is 3 squared plus 4 squared equal to this entire hypotenuse. Notice they don't give us this segment, but isn't this a radius? Yeah, so this is actually 3. So my hypotenuse is 3 plus 2, so this is 5. I don't even need to apply it. This is a Pythagorean triple. Yep. This is going to work out. This is a right triangle, and so then we must have a tangent segment. All right. ST here, they're going to ask, they say ST is tangent to circle Q, find the radius. So r squared plus 24 squared is going to equal r plus 18 squared. All right, r squared, 24 squared, I can tell you is 576. And then this here, I'm going to FOIL that out, and I would, again, my r's would cancel. I'm close to the end, so I'm not going to do that one any further. Just the setup on this one, x squared equals 9, so x equals plus or minus 3, but only 3 makes sense. Done.